study of diode rectifier. A diode rectifies an AC voltage so that it can be smoothed and converted into a DC voltage. Okay, that means when diode convert your AC voltage to a DC voltage, there are usually lots of noise. Sometimes it's called ripples and noise. So we need to remove those noise and ripples so that we can get a pure DC. So we need to smooth it and convert it into a pure DC voltage by using some filter circuit. Okay. So a rectifier, however, can produce a constant or variable DC voltage. A diode rectifier can produce a fixed DC voltage, whereas a SCR can produce a variable DC voltage. Okay. Now, this is the introduction. The objective of this lab are to study half-wave rectifier, okay, and study full-wave rectifier. Diode rectifiers are of the following types: half-wave rectifier, full-wave rectifier, bridge rectifier, okay, and center-tapped full-wave rectifier. So we'll study these three types of rectifier circuit. Rectifier, however, cannot produce a smooth DC voltage. So the rectification block that makes the output DC voltage a smooth one follows a filter circuit. So first we design the rectifier circuit by using the diode, then we use a filter circuit to get a smooth DC output. In this case, the capacitor acts as a smoothing filter so that the output is nearly a DC voltage. If filtering is not perfect, there will be a remaining voltage fluctuation known as ripple on the output voltage. The half-wave voltage signal is normally established by a network with a single diode has an average or equivalent DC voltage level equal to 31.8% of the peak voltage, whereas the full-wave rectifier signal has twice the average or DC level of the half-wave signal, or 63.6% of the peak value. Now, this is the working principle of half-wave rectifier. Look at over here. This is the AC source. This is a single diode. This positive side is the anode, negative side is the cathode, and this is the load resistance. So when we supply the AC voltage, the positive half cycle can conduct, because during the positive half cycle, this diode is forward biased and it can conduct, and at the output we get the positive half. In the negative half cycle of the input voltage, AC voltage cannot conduct, so negative half is removed. So negative cycle is removed. We don't get the negative side at the output because diode becomes reverse biased at that time. Okay. So in this website is called half-wave rectifier. Only we can rectify the half-wave, not the full wave. Next is the full-wave rectifier and center-tap bridge rectifier. I will use some animation to explain these two concepts. Then we'll go to the practical one. So this is the full-wave bridge rectifier. Look at over here. This is the full-wave AC voltage at the input, and there are 4 diodes. At a particular time, only 2 diodes conducts. Okay. Where supply voltage is applied negative and positive over here. You see. Look at over here. This is the conduction. Okay. Again. You see. Supply voltage positive and negative. Okay. So this is the transformer, and this is the step down transformer according to a need. Okay. So when this positive cycle of the AC voltage is applied, this point is positive, and when this point is positive, look at over here. This diode D1 is forward biased. So current flows through D1 to the load, again to D4. So D1 and D4 conducts in the positive half cycle. Okay, so we get the positive half cycle at the output. Now, look at over here. Okay. When the negative half cycle, look at over here. This is negative and this one is positive. In that case, this D1 and D4 reverse bias, so they cannot conduct. But this D2 and D3, they are forward bias because negative side on the cathode and positive side on the anode. So D2 and D3 are forward biased, so current conducts. Again, current conducts on the same direction over here. Okay, so we get a full wave rectification, both positive cycle and negative cycle at the output. Okay, this is the input and this is the output. So if I again run the animation, look at over here. So this is the full wave rectifier circuit, bridge rectifier circuit. 4 diodes has been used at a time, only 2 diode conductors, and we get full rectification. Now is the bridge rectifier circuit. In a center type bridge rectifier circuit, we don't use 4 diodes. Instead of 4 diodes, we use only 2 diodes. By using only 2 diodes, we are going to do the rectification. So let's see how it works. Okay, this is the step down transformer. We do the step down depending on our voltage requirement at the output. And 2 diodes has been used, diode 1 and diode 2. Okay, and this is the load. And if you look at the center of the output side of the transformer, okay, there is a center tap. This is the center tap. Okay, the load is connected to the center tap. So 2 diodes has been used, 1 over there, and this is the ground point or 0 voltage of the center tap transformer. So this now let's see how it works. We apply the AC voltage at the input. When positive negative voltage is applied, then S1 get negative and S2 get positive. Okay, look at over here. Animation, polarity is changing. Let's investigate the positive half cycle. Positive voltage has been applied at the input. So S1 is getting the positive value, G is getting the 0 value, it's ground, and S2 is getting the negative voltage. So when S1 is positive, diode D1 is forward biased, and because S2 is negative, diode D2 is reverse biased. So here when the diode is forward biased, it allows the current to flow through the load. Diode 2 is reverse biased, so it does not allow the current to flow. So look at over here, current is flowing through diode 1 from point A to B. That's the positive half cycle of the input AC voltage. Now, when we apply the negative half cycle of the AC input voltage, S1 become negative in polarity and S2 become positive in polarity. So look at over here. Because S1 is negative, diode 1 is reverse biased. So it cannot conduct. G is the ground on 0 voltage. Now, since S2 has the positive polarity, diode D2 is forward biased and diode 1 is reverse biased. So diode 2 conducts and current flows in the same direction from A to B. And it's the negative half of the AC input voltage. Okay, so what we see, as the input voltage changes the polarity, at the output we get both positive and negative side of the same side. That means we get a DC output. That means we rectify the both sides, both positive half and negative half. So it is called fuller center tap bridge rectifier. So it is doing the full of rectification. Look at the changing polarity of the input voltage, AC voltage, and accordingly, each diode is taking one half. Diode 1 is taking positive half, and diode 2 is taking the negative half of the input AC voltage. And finally, at the output, we get a fuller rectification. So, any question over here? Have you understood? Okay. So, we'll move to the next part. Now is the time to do some practical activity. Okay. So, there's our area to do some practical activity. Is the online multi-sim simulator. As you have done in the last lab, all of you log into the NI Multisim Live. Okay, all of you log in to the NI Multisim Live. Open up your browser and log in to the Multisim Live. Already have done in the last lab. Okay, so let me log in, and as I log in, all of you do the same thing. So I'm logging to my NI user account by using Multisim Live. Okay, so that I can create the circuit. All of you log into your Multisim Live and click the button Create Circuit. We'll implement all the three circuits: half wave rectifier, full wave bridge rectifier, and center tap full wave rectifier. All three circuits we are going to implement over here. So when you log in, give me a feedback that okay, you have logged in, so that I can go to the next step. Okay. So all of you, what you need to do, click the button Create Circuit. Create Circuit. So when you click the button Create Circuit, it will allow you to enter your design and simulate. So it is initializing Multisim Live, waiting for some awesome. Okay, here we go. This is our design window, and this is the components on the left side that you can pick. So first we are going to do let's add something. Half wave rectifier. Half half wave rectifier. So let's okay. Now, first thing we need to have the AC input voltage. This is source, click the source on the left side, AC voltage. Okay. So look at over here. Let's take 24 volt. Okay. 24 volt. You can take other voltage supply and frequency 1 kilohertz. Change the frequency to 50 hertz. Okay. 1 kilohertz will be too fast to visualize. Okay. So let's say 50 hertz so that we can visualize. Okay. Voltage offset 0 volt. Okay. Phase shift 0. Okay. So we have chosen a voltage source of 24 volt and frequency 50 hertz. AC voltage source. Okay. Now we'll pick up the diode. Diode. Okay. Then we are going to pick up the load. Let's say 10 kilo ohm load. Let's pick up the load resistance. Resistor. Let's rotate so that we can connect. And what value? 10k. Give a value 10k. 10 kilo ohm resistance. Okay. Now is the time to make the circuit complete. So move your mouse. It is hand shape, and to the point you want to join the wire. Your hand shape will get changed to a roll of wire. So click on the point, drag and drop to connect. Again, click, drag and drop to connect. And to again. Okay. So we have made the wire connection. Only thing is left, we need to ground it. Okay. Ground it. This is ground. And connect the ground. Okay. So our circuit is complete and ready to simulate. Ground from here. This is this ground. So all of you have done the circuit design. A AC voltage source, a diode, the load resistance R1 10 kilo ohm. Finally, we connect the wires and we put a ground. Okay. Now to visualize the wave shape, we need to connect the probe. Analysis and annotation. Click the probe, voltage probe. Connect one probe at the load and connect one probe at the voltage. Input to AC voltage, so that you can compare what we are getting. Okay, now is the time to simulate. So all of you have done. Okay, I am waiting. So this is our half-wave rectifier circuit. Now is the time for simulation. So we'll choose the option split so that both at the same time we can see our circuit plus the simulation data. Okay, so click the play button, run simulation, Control R. Look at over here. Let's I think do some scaling. Otherwise, we cannot see. Okay, so let's stop the simulation and go over here. Come over here. Minimum maximum voltage. Okay, time second. Minimum voltage and maximum voltage. Let's change. Minimum voltage is 0. I think minimum voltage is minus. It is 24, right? Minus it is 12 volt. Okay, we have taken 24 volt. We have taken. Okay, so let's take minimum minus 24. Let's say minus 24 and maximum 24. Okay, maximum let's say 4 second or 1 2 second. Okay, so let's run the simulation. Look at over here. We are getting something. One is that is fluctuating. I think we can again make it a little bit more visible. Let's stop it and let's reduce the time. Increase the time. I think minimum 0, maximum now it is 1 millisecond per division. Okay, so I think increase the time. I think it will be more easier to visualize. Okay, it's this one. So what we see, this is the rectified voltage we are getting in, and this is the input voltage. Okay, input voltage is fluctuating. I think let's bring the wave shape in a smaller place. Okay, or let's change the frequency. So look at over here. This is the output we are getting. DC voltage we are getting, and this is the input AC voltage. And let's change the timing. I think then it will be more better shape we'll see. Okay. Time we want to see about both side. Okay, so what we can do, we can division. Okay, time what division it is showing. So what we see over here, if we just pause it, you see this is the output we are getting. Okay, and this is the input. Let's say do auto. Let's run the simulation. Look at over here. Now it is visible. So what we see over here, you see 50 millisecond per division we have taken. So look at over here. This is the input AC voltage. Okay, and we see only this positive half is rectified. So look at over here. If I just this is the input voltage. Okay, AC voltage. Okay, and this is the rectified output. Now this rectified output is not pure DC. You see, it looks like half sine wave. So we need to filter, add a filter circuit. Okay, we need to add a filter circuit to get a pure DC. Now what we are going to do, we are going to add the filter circuit because this is actually not useful. These are noise. Okay, we need to smooth it and we want to get a pure DC. So what we need to do, let's start the simulation. Go to the design window and add the filter circuit. So we'll use a filter circuit by using a capacitor. So let's pick up a capacitor. This is the capacitor. So put a capacitor at the output of the load. This capacitor acts as a filter circuit. Okay. So let's take a value 47 microfarad. Acting in our lab sheet, we have this 47. Okay. So let's do it. Let's connect the wire. Okay. Now let's see what happens. I think we want to see some improvement, right? We want to get close to a DC voltage because to make again pure DC again more filter element need to add. Okay, in the real one they use more multiple capacitor, multiple filter element. Okay, but let's see this simple filter circuit with a capacitor. Let's run the simulation and let's check the grapher. Look at over here now. You see, this is our input voltage. Now look at over here. This is the DC. Much better a DC signal we have got. Okay, much better DC signal we have got now. Let's stop the simulation. See, look at over here. These are DC voltage. Okay, these are AC input. Okay, but when we get the DC, you see, these are DC voltage. Okay, so much better DC voltage output we are getting by using a simple capacitive filter circuit. Okay, so this is our first experiment of rectifier. Now again go to the design window. Again, second step, the full wave bridge rectifier. Okay, now we'll do full wave bridge rectifier. Full wave bridge rectifier. Full wave rectifier, or you can call a full wave bridge rectifier.
So, I have a question.
Yes. Yes. What is the question?
Sir, I'm something that useful signifier.
Okay. In that case, only thing you need to check, you see the simulation grapher. Okay. When you choose the grapher,
The graph is okay, sir. But the voltage V1
now I have look at over here, minimum, maximum. I have given minimum in the grapher minus 50, maximum 50. Have you done it like this?
Yes, sir. Yes, sir.
Okay, then this trigger normal. I have given trigger normal.
Take the time, sir. I will get the sir. I will set the time, sir.
Timing actually I set it automatic. Look at over here, trigger. It's a normal. And let me do the simulation. I think it will be easier to understand. From the simulation window, look at over here. You see time per division. I have chosen this one. 50 millisecond per division. Click this one, then you can change it. 100 millisecond per division. 50 millisecond per division. Okay, so you can change it over here. Again, let me show you. Run the simulation. This is time per division. Just change it. 20 millisecond per division. This is. If
Yes, sir. Yes, sir.
50 millisecond per division. Okay. So this is like an oscilloscope. Okay, the oscilloscope. This is like the oscilloscope, and you are changing the time per division. Okay, so that you can visualize it clearly. So this is your input. Okay, so when you simulate, change that time division. Okay, click the simulation. Yes, this one, right? Okay, so do it. So if you click a single trigger, I think it will do the same job. So let's proceed to the next step. Our next design is the full wave bridge rectifier. In this case, we are going to use 4 diode. Okay, so let's delete the connection. Delete the connection. Okay, so take 4 diode. One diode, just copy the diode and place it over here I think to that I need to place like this. Just rotate. Okay. To that over here, I can copy the diode. Now connect the wires. Okay. You have used 4 diodes. Okay. So now connect the load. At this time, just to remove this. Okay. So we have designed our full bridge rectifier circuit. There are 4 diodes. Now at the probe, at the output of the load, at the probe voltage, and another probe to check the input AC voltage. Okay, so all of you are done. Okay, complete, finish it. Then we will go for simulation. Time for the simulation now. So go for simulation, grapher, and look at over here. This is the input and this is the output we are getting. And look at the output voltage. 22.529 volt. Much higher voltage we are getting than the previous design. Okay, half a rectifier. Half a rectifier, I think the voltage we get, look at over here. You see? The half-wave voltage signal is normally established by a network with a single diode and has an average or equivalent DC voltage level equal to 31.8% of the peak voltage. Whereas the full-wave rectified signal has twice the average or DC level of the half-wave signal, 63.6% of the peak value. So much higher voltage we get when we do the full-wave rectification. And you can see it over here. In our simulation, you see, look at the value, 22.7 volt. And the peak value is 23.102. That means we are getting close to the peak voltage of the input signal over here. Our peak input voltage is 23.3 volt, and we are getting this peak is 22. So if average, I think it becomes you can it will come close to 20. Okay, look at over here. This is below is 21. So average below is 21. Average will come more than 21, close to 22. Okay, average will come close to 22. So very good voltage we are getting. Okay, at the output. Okay, so it has a very good efficiency. Okay, so this full of rectifier has a very good efficiency. You see, look at over here. Input is 24 volt AC, okay, and output we are getting 22.5, around 22 volt average. So very good efficiency this circuit is giving. Okay, so that's the full bridge rectifier. Now we will do center tap. Okay, center tap rectifier circuit. So again, we don't need 4 diode. So center tap, full of
So yeah, back and forth
this. Okay, your screen, if you use a smaller screen, then you'll see there is an arrow on the bottom. You'll see. I think you'll see there's a arrow on the bottom. So if you move the cursor, I think it will pop up. Okay, just hover your cursor, it will pop up. It is automatically adjusting the screen depending on your window size, screen size. Okay. So let's see, next is the center tapped full of rectifier. Rectifier. This center tapped full of rectifier circuit. So now in this case, we are not going to use 4 diode, only 2 diode we need. Okay. So let's delete some diode. Again, first delete all the wires so that we can do our design. Only 2 diode we need. Okay. Delete the wire. Okay. Now we have the single source, 2 diode. One thing we need is center tap transformer. Okay. So let's pick up the center tap transformer. Transformer. Okay. Click the resistor symbol. Then it will give you the option for transformer. So click the transformer and you'll find IPIS with center tap. Okay. So pick up the center tap transformer. 1P, 1S. So with center tap. Primary, secondary with center tap. Okay. So this is the description. Configurable transformer. Okay. So let's place the source. So connect it.
So, modern rectifier
The frequency you can change. Okay. Only thing you need to visualize is just change the time per division. Then you can visualize it clearly. The frequency, different frequency have you can use. Okay. Don't worry. Depending on the need, the frequency can be different. To visualize properly, only you need to set the oscilloscope. That means time per division and the magnitude of the voltage need to set up so that you can visualize this nicely. So this is the center tap transformer. This is the supply voltage, and this is the 2 diode. Okay, so let's connect the diode, and this is the load resistance. So connect the load in the center. Bring the load, rotate it, connect it to the center tap. Okay, and bring one diode on the top. Do the connection. Okay, then bring another diode on bottom. Do the connection. Then connect with the load. Okay, other side. Okay, so this is a center tab. We can use a capacitor across the load. We can do it later. Okay, first we see the output. So we don't need extra ground over here. Let's look at your left sheet and follow the left sheet diagram. Okay, they have used resistor and capacitor. Okay, that's fine. Okay, let's see how it works. Okay, so let's do the grapher. Let's see how it works. No ground node. Okay, so in stick up done, we need to give the ground node. No ground node was found in your circuit. To ensure accurate simulation, add a ground component and simulate again. So go for the design again. Let's take the simulation, add a ground over here. Let's say. So what is over here? If I go to the design, this is our prop 2 and this is our prop 1, green color. Okay, I think the thing is like that. This is 0 voltage, right? This one is 0 voltage. So we need to measure voltage across this resistor. So make your circuit complete like this. Okay, use a capacitor and take voltage measurement at this point. I think you put a ground over here. Okay, put a ground over here at the source and at a capacitor over here. So let's do it. 228 microfarad capacitor across the load. Okay, 1 kilo ohm load and a ground over here. Yes.
Sir, voltage source is bottom.
No. Look at over here at a capacitor. Look at the diagram. You see, take a capacitor of 228 microfarad across the load, okay, and measure voltage at this point. Otherwise, if you measure voltage over here, it is 0 voltage, okay. You need to measure voltage from here, and you need to take a measurement from here because this is the input to the input AC, okay. This diode 1 and diode 2. So keep a voltage probe over here, okay, and use a capacitor. Okay, and use another probe to measure voltage. Now let's go for simulation. So we have used a smoothing capacitor of 228 microfarad across the load. Load is 10K. You can change it. So let's go for the simulation now. You see, now we are getting a nice voltage. Okay, this is our output. Uh, sure, probe only output. Let's say let's give a probe to our input. Okay. So let's run the simulation. You see this the input voltage. I think we can little bit. I think it needs to change the magnitude. Minimum. I think now you can see it more nicely. Okay, so this is our input, okay, and a very nice smooth voltage output we are getting because of the capacitor, okay. You see, look at the quality of the DC voltage, almost perfect. Okay, very nice the software getting. This is your input. This is your DC, almost without any noise. Okay, very good DC quality. And this is your input. Okay, this is your input, and this is your output. Very good quality voltage we are getting because of capacitor, smoothing capacitor. So that's the center tapped fuller rectifier. All of you have done.
So, in our source, so voltage should be the connected to the negative.
No, that doesn't matter. It does not matter. It does not matter because this is AC voltage. Okay, one time it will become positive, other time it will become negative. So next time it will become positive, negative, negative, positive, something like that. This is alternating current. Okay, so it's okay, no problem. So all of you have got the nice output like this, a pure DC output. Okay, almost perfect. Why not? What mistake you have done?
I'm not sure. If I am to until
Okay, use the mic capacitor. By changing the capacitor, you can see the effect. Okay, let's change the capacitor value. Let's see how it works. Let's change it to 47 microfarad. Let's see how much is putting it needs 47 microfarad. And now let's do the simulation. You see, now we are getting some ripple. If you are getting less below capacitor, you are getting some ripple or noise. But if you increase the capacitor value, let's say increase the capacitor value over here again, let's say 300 this time. Because of capacitor is smoothing. If you give the higher value of capacitor, then I think it will smooth more. Let's say give 300 microfarad. Okay, so let me run the simulation. To the grapher. Now look at over here. If you look at over here, almost it looks like very smooth curve. Okay, so there is no noise, very little noise actually. If you there very little noise because curve is almost smooth, so noise is very little. You almost close to pure DC. Now let's stop the simulation. Go to the design. Change the capacitor value to let's say 30 microfarad. 30 microfarad. Now let's run the simulation again. Now look at over here. This is your output. You see, this is your output. And look at over here. There is zigzag. Up, down, up, down. That means there are noise. This is the noise. A DC voltage cannot be up, down like this. It's a 12 volt DC, okay? Or 5 volt DC. Fixed voltage. But there are up, down. You see? Up, down in the voltage. So it is not a pure DC. These are called noise or ripple. Ups, down, okay? This is the ripple or noise. So this is not desirable in this, okay? If you get sometimes 4.5 volt, instead of 5 volt. Sometimes 5.5 volt, not good. 5 volt means pure 5 volt. So in this case, you are not getting pure DC output.
So আপনার যে 0 থেকে শুরু হয়ে 580 পর্যন্ত এসে না,
Yes.
আমার just 580 শুরু হয়েছে, এখানে আসে।
Okay, now look at over here, scaling. You see, minimum, maximum. It's just a scaling.
Sir, range increase যাচ্ছে।
Minus 1.5 volt, and this is maximum 1.5 volt. And you see, ripple or noise. I think we can try this one. Single trigger. Let's run the simulation. Okay. They are noise. Okay, these are noise because of capacitor. And also, you can change it from here. Okay. So these are the noise because of capacitor. So if you change the capacitor again, let's give a larger value. Let's 400 microfarad. Let's see how smooth we get. Okay. No, not this one. Capacitor. Means 300. Last time we had 300. Okay. Now let's give 400 microfarad. Let's see what happens. You see, look at the distance. So nice DC voltage we are getting. You see, almost a straight curve. Very little fluctuation. Okay, this is a good output because fluctuation is very low. So in this way, by using the filter circuit, you can smooth your DC output to remove the noise and record. Input AC, output DC, fixed voltage. So that's the advantage of using filter circuit.